Imagine gazing at a photograph that captures the end of time itself, a snapshot of a realm where, according to Einstein's theory of relativity, time ceases to exist. This haunting image isn't a scene from science fiction, but a concept rooted in the mind-bending predictions of general relativity. Einstein's equations describe regions of spacetime so warped that they form black holes, where gravity is so intense that time itself comes to a standstill. These cosmic enigmas, known as singularities, challenge our understanding of reality and beckon us to explore the edges of physics. But what if scientists on Earth, in a lab on US soil, briefly tore open the fabric of the universe? What if they created something that vanished before anyone could fully grasp its implications? Recent rumors surrounding Fermilab, one of the world's premier particle physics laboratories, have sparked intrigue and speculation. While these claims are unverified, they point to a deeper truth. Humanity is on the cusp of unlocking secrets about the universe that could redefine our understanding of spacetime, quantum mechanics, and the very nature of existence. This exploration dives into the fascinating world of quantum simulations, vacuum physics, and theoretical constructs like wormholes and cue balls, revealing how cutting-edge science is pushing the boundaries of what's possible, without crossing into the realm of sensationalism or violating YouTube's community guidelines. Join us as we unravel the mysteries of the cosmos, grounded in real science and the latest discoveries as of July 24th, 2025. In recent years, whispers have circulated in online physics forums and social media about a startling possibility that Fermilab, located in Batavia, Illinois, accidentally triggered a stable hole in the fabric of reality. These rumors, while unconfirmed, gained traction after anecdotal reports surfaced about unusual diagnostic spikes during a 2021 beam pulse at the facility. Some claimed that sensors registered anomalous readings that couldn't be explained by standard particle interactions, hinting at something extraordinary. Others spoke of a mysterious data blackout during a late-stage test involving legacy equipment from the Tevatron, Fermilab's now decommissioned particle accelerator. These accounts suggested gaps in measurements where data simply didn't register, fueling speculation about exotic spacetime phenomena. Let's be clear, no official documentation from Fermilab or peer-reviewed scientific literature supports these claims. The Tevatron, which operated from 1983 to 2011, was shut down long before these alleged incidents, and its equipment is used only for specialized legacy experiments today. Equipment failures in complex facilities like Fermilab are not uncommon and could easily explain such anomalies. However, the persistence of these rumors reflects the public's fascination with the idea that we might be on the verge of manipulating spacetime itself. What makes these stories compelling is their connection to real, groundbreaking work in quantum physics and vacuum dynamics. Advances in quantum simulation, particularly at Fermilab, have blurred the line between theoretical models and physical reality, raising profound questions about what's possible. Could a simulation inadvertently influence the real world? Could we be approaching the ability to create or detect phenomena once thought to exist only in equations? Let's dive into the science behind these ideas and separate fact from fiction. In late 2022, a team led by Fermilab scientist Joseph Liken made headlines with an extraordinary experiment. Using Google's Sycamore quantum processor, one of the most advanced quantum computers in existence, they simulated a traversable wormhole. Wormholes, hypothetical tunnels in spacetime that could connect distant points in the universe or even different universes, have long been a staple of theoretical physics and science fiction. Einstein's general relativity predicts their existence, but creating one physically would require exotic matter and energies far beyond our current capabilities. What Liken's team accomplished was nothing short of remarkable. They used quantum computing to model the behavior of information traveling between two entangled quantum systems, mimicking how it might move through a wormhole. Here's how it worked. The team encoded quantum information at one point in their system and observed it emerging at another, a process known as quantum teleportation. This wasn't a physical hole in spacetime, but a mathematical construct that behaved identically to a theoretical wormhole. The quantum bits, or qubits, followed the precise equations that govern how matter or energy would traverse a real spacetime tunnel. What's more, the simulation remained stable long enough to be measured and studied, a feat that stunned the scientific community. As reported by The Guardian, no physical rupture of spacetime occurred, but the mathematical fidelity of the simulation was uncanny. This experiment marked the first time scientists had created a quantum system that mirrored the behavior of a traversable wormhole, bridging the gap between between quantum physics and gravity, two realms that have eluded unification for decades. The implications are profound. If we can simulate stable wormholes in a quantum computer, what other exotic spacetime phenomena might we model? Black holes, vacuum decay, or even the birth of the universe itself could be within reach. These simulations don't just satisfy scientific curiosity, they allow researchers to test theoretical predictions in controlled environments, explore boundary conditions, and assess potential risks without manipulating physical reality. Lincoln himself emphasized the distinction between theory and reality, noting that these experiments are about understanding what's possible, not creating dangerous phenomena. Yet the success of this simulation has fueled speculation about whether such digital models could ever influence the physical world, a question we'll explore further. To understand the rumors and the science behind them, we need to delve into the concept of a vacuum in physics. Contrary to popular belief, a vacuum isn't just empty space. It's the universe's baseline energy state, a seething sea of quantum fluctuations where particles and antiparticles pop into and out of existence. But what if this vacuum isn't the lowest possible energy state? What if there's a deeper, more stable state, a true vacuum that our universe hasn't yet reached? This idea, known as vacuum metastability, suggests that our universe might exist in a false vacuum, like supercooled water that's below freezing but hasn't yet turned to ice. A sufficiently energetic event could, in theory, trigger a transition to this true vacuum, creating a bubble where the laws of physics differ. This concept ties into another theoretical construct, the cue ball. Proposed by Nobel laureate Sidney Coleman in the 1980s, cue balls are stable lumps of scalar field energy that could form in certain supersymmetric theories. Unlike unstable particles that decay quickly, cue balls are non-topological solitons, coherent structures that could persist indefinitely under the right conditions. In the context of particle physics, a cue ball might appear as a spherical region where the Higgs field, which gives particles mass, becomes locally condensed. To detectors, this could register as a hole in space-time, where physical laws deviate subtly from the norm. Could Fermilab's high-energy experiments have accidentally created such a structure? The facility's particle accelerators operate at energies far below those of cosmic rays, which bombard Earth constantly with no catastrophic effects. However, the precise control of fields in a collider might, in theory, create conditions impossible in nature, potentially allowing exotic structures to form briefly before collapsing. Another intriguing possibility arises from the study of causal structure theory, which examines how information propagates through space-time. In conventional physics, every point in space-time has a light cone, a region defining where light, and thus information, can travel. These light cones underpin causality, ensuring that cause precedes effect. But at extremely high energy density, such as in particle colliders or the early universe, these causal structures might deform. Recent theoretical papers, including those published on airquiff.org as of July 2025, explore scenarios where localized regions of spacetime experience causal disconnection. In such regions, the normal rules of particle and field interactions could change, creating a bubble where light cones are altered or detached from the surrounding universe. Imagine a small volume of space where time slows, distances stretch, and information can't flow normally to the outside world. To an observer, this might appear as a black patch, a hole in space-time. If Fermilab's sensors detected a region where signals vanished or behaved anomalously, it could indicate such a phenomenon. These events would be fleeting, lasting less than a trillionth of a second, but their detection would provide experimental evidence for theories that have remained speculative for decades. Importantly, gravitational effects, as outlined by Coleman and Frank DeLucia in their 1980 paper on vacuum decay, would prevent such bubbles from growing. The immense gravitational gradient at their boundaries would cause them to collapse almost instantly, acting as a cosmic safeguard against runaway instabilities. If exotic phenomena like cue balls or causal rifts could form, why haven't they destroyed the universe? The answer lies in the elegant mathematics of gravitational collapse. Coleman and DeLucia's work demonstrates that any vacuum bubble small enough to be created in a lab would be too tiny to overcome its own gravitational forces. These bubbles would collapse faster than they could expand, ensuring no threat to the universe. Cosmic rays, which carry energies millions of times greater than those produced at Fermilab or CERN, provide further reassurance. These natural particles have bombarded Earth for billions of years, creating collisions far more energetic than any human-made accelerator. Yet, the universe remains remains intact, suggesting that such phenomena, even if briefly created, pose no existential risk. This cosmic immune system doesn't diminish the importance of studying these phenomena. Fermilab's shift toward quantum simulation reflects a strategic evolution in physics. As physical accelerators reach practical limits, quantum computers like Sycamore offer a new frontier. By modeling extreme conditions, black hole horizons, wormhole interiors, or vacuum transitions, these simulations provide insights into phenomena that are impossible to observe directly. They also allow scientists to assess risks, refine theories, and explore edge cases without endangering reality. This approach isn't about fear-mongering, it's about pushing the boundaries of knowledge while maintaining safety and integrity. Let's set the record straight. No stable hole in the universe was created at Fermilab. The quantum wormhole experiment was a simulation, not a physical space-time tunnel. Claims of vacuum bubbles or causal rifts lack credible evidence and stem from misunderstandings or unverified anecdotes. Fermilab's detectors, designed to capture the tiniest deviations in particle behavior, would have documented any genuine anomaly, and such findings would be rigorously studied, not concealed. The scientific community demands extraordinary evidence for extraordinary claims, and no such evidence exists. Instead, Fermilab is advancing our understanding of the universe through groundbreaking research. The deep underground neutrino experiment, DUNE, is probing the mysteries of neutrinos, ghostly particles that could reveal why matter dominates over antimatter. The muon G2 experiment has detected anomalies in muon behavior, hinting at new particles or forces beyond the standard model. Dark matter detectors are searching for the elusive particles that make up roughly 27% of the universe's mass energy. These projects, while less sensational than fictional portals, are unraveling real mysteries that could reshape physics. The success of Fermilab's wormhole simulation underscores the transformative potential of quantum computing in physics. Unlike traditional computers, which process information in binary bits, quantum computers use qubits that can exist in multiple states simultaneously, thanks to the principles of superposition and entanglement. This allows them to tackle complex problems, like simulating the behavior of spacetime under extreme conditions with unprecedented precision. The Sycamore processor, with its ability to perform calculations in feasible for classical supercomputers, enabled Likken's team to model a wormhole's information transfer with remarkable accuracy. This wasn't just a theoretical exercise, it was a proof of concept that quantum systems can replicate the mathematical behavior of exotic spacetime phenomena. As quantum technology advances, we may soon simulate entire black holes or cosmic phase transitions, providing insights into the universe's earliest moments or the conditions near a singularity. These simulations are safe, controlled, and free from the risks associated with physical experiments, making them an ideal tool for exploring the unknown. To put Fermilab's work in perspective, consider the natural laboratory of the universe itself. Cosmic rays, high-energy particles from supernovae, black holes, and other cosmic phenomena strike Earth's atmosphere with energies far surpassing those of any human-made accelerator. Some of these particles carry energies up to 10 to the power of 20 electron volts, millions of times greater than the Tevatron's peak of 1 tera-electron volt. These collisions, occurring naturally for billions of years, have never triggered a catastrophic vacuum transition or stable spacetime anomaly. This cosmic evidence reinforces the theoretical safeguards outlined by Coleman and DeLucia, suggesting that even if exotic phenomena like cue balls or causal rifts could form, they would collapse harmlessly. Fermilab's experiments, operating at far lower energies, are thus unlikely to pose any risk. Instead, they provide a controlled environment to study the fundamental laws that govern these natural processes, offering clues about the universe's stability and evolution. The allure of stories about holes in the universe reflects humanity's deep desire to understand the cosmos, even at its most mysterious and intimidating edges. Fermilab's work, from quantum simulations to neutrino research, embodies this quest, blending bold exploration with rigorous caution. Every experiment is designed with safety in mind, guided by decades of theoretical and observational evidence that our universe is resilient. The rumors of spacetime rifts may capture the imagination, but the real story is far more more inspiring. Scientists are using cutting-edge technology to probe the fundamental nature of reality, from the subatomic to the cosmic scale. As we stand on the brink of new discoveries, quantum simulations and particle physics are opening doors to questions we've only begun to ask. Could we one day confirm the existence of extra dimensions? Could we unravel the mysteries of quantum gravity? The answers lie not in sensational tales, but in the meticulous, collaborative work of researchers worldwide, and Fermilab is at the forefront of this journey. The marriage of quantum mechanics and general relativity remains one of the greatest unsolved challenges in modern physics, and Fermilab's quantum simulations are a critical step toward this unification. Quantum mechanics governs the subatomic world, where particles behave like waves, and entanglement creates instantaneous connections across vast distances. General relativity, on the other hand, describes the large-scale structure of spacetime, where gravity warps the fabric of the universe. These two frameworks are extraordinarily successful in their respective domains, yet they remain fundamentally incompatible. The wormhole simulation conducted by Licken's team offers a tantalizing glimpse into how these realms might be reconciled. By using quantum entanglement to mimic the information transfer through a spacetime tunnel, the experiment demonstrated that quantum systems can replicate gravitational phenomena, at least mathematically. This breakthrough has profound implications for theories like string theory and loop quantum gravity, which propose that spacetime itself may emerge from quantum processes at the smallest scales. As of July 2025, ongoing research at Fermilab and other institutions is leveraging quantum simulations to explore these ideas further, testing whether the fabric of spacetime could be quantized into discrete units, much like energy in quantum mechanics. These efforts are not about creating physical wormholes or black holes, but about understanding the underlying principles that govern both the quantum and cosmic realms. By simulating conditions that mirror the early universe or the interiors of black holes, scientists are piecing together a unified picture of reality, one that could reveal whether our universe is a single continuous whole or a tapestry woven from countless quantum threads. While quantum simulations are stealing the spotlight, particle accelerators like those at Fermilab and CERN remain indispensable tools for probing the universe's fundamental building blocks. These massive machines accelerate particles to near-light speeds, smashing them together to create conditions akin to those fractions of a second after the Big Bang. The Tevatron, Fermilab's flagship accelerator until its shutdown in 2011, played a pivotal role in discovering the top quark and constraining the properties of the Higgs boson, both cornerstones of the standard model of particle physics. Today, Fermilab's focus has shifted to next-generation experiments like DUN-E and muon-G-2, but the legacy of accelerators lives on. These experiments rely on the precise control of particle beams to study elusive phenomena, such as neutrino oscillations or magnetic anomalies that could hint at physics beyond the standard model. Unlike the speculative scenarios of space-time rifts, these experiments produce tangible, measurable results that push our understanding forward. For example, the muon-G2 experiment's detection of a discrepancy in the muon's magnetic moment suggests the influence of unknown particles or forces, potentially opening a window into new physics. Meanwhile, Dune's ambitious goal of sending neutrinos 800 miles underground to detectors in South Dakota could unlock secrets about the matter-antimatter asymmetry that allowed our universe to exist. These projects highlight the complementary roles of accelerators and simulations. While accelerators probe the physical world directly, simulations allow scientists to explore theoretical scenarios that are currently inaccessible. Together, they form a powerful toolkit for unraveling the universe's mysteries, ensuring that every step forward is grounded in rigorous data and theoretical insight. As we push the boundaries of physics, questions of ethics and responsibility come to the forefront. The rumors about Fermilab creating a hole in the universe, while unfounded, raise important considerations about the risks and rewards of high-energy physics. The scientific community has long grappled with these concerns, particularly in the context of particle accelerators. When the Large Hadron Collider, LHC, at CERN began operations, some speculated that it could create microscopic black holes or trigger vacuum decay, scenarios that were thoroughly debunked through theoretical calculations and cosmic ray observations. Fermilab's experiments, operating at lower energies than the LHC, are subject to even stricter scrutiny, with safety protocols informed by decades of research. The Coleman-Delucia mechanism, which ensures that vacuum bubbles collapse harmlessly, is just one example of how theoretical physics provides reassurance about the safety of these experiments. Beyond technical safeguards, the ethical imperative of transparency drives the scientific process. Fermilab and other institutions publish their findings openly, subjecting them to peer review and public scrutiny. This openness counters misinformation and ensures that speculative claims, like those about space-time rifts, are met with rigorous evidence or dismissed. As we advance into an era of quantum simulations and potentially transformative discoveries, the physics community remains committed to balancing curiosity with caution, ensuring that our quest to understand the universe respects the safety and integrity of our world. This ethical framework, combined with the relentless pursuit of knowledge, underscores why institutions like Fermilab continue to inspire awe and trust as they explore the frontiers of science. Fermilab's ongoing efforts to unravel the mysteries of dark matter and neutrinos represent some of the most promising frontiers in modern physics, offering potential insights into the universe's composition and evolution. Dark matter, which accounts for approximately 27% of the universe's mass energy, remains one of the greatest unsolved puzzles in cosmology. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it detectable only through its gravitational effects on galaxies and cosmic structures. Fermilab's dark matter detectors, such as those in the Cryogenic Dark Matter Search, CDMS, and other experiments, are designed to capture the faint signals of dark matter particles, such as weakly interacting massive particles, WIMPs, as they pass through Earth. These experiments use ultra-sensitive detectors deep underground to shield them from cosmic rays and other background noise, increasing the chances of detecting these elusive particles. Meanwhile, the deep underground neutrino experiment, DUNE, is pushing the boundaries of neutrino physics by studying these nearly massless particles that interact so weakly with matter that trillions pass through our bodies every second. By firing a beam of neutrinos from Fermilab to detectors in South Dakota, DUNE aims to uncover why the universe contains more matter than antimatter, a fundamental asymmetry that allowed stars, planets, and life to form. Recent results from DUNE's prototype detectors, reported in scientific journals as of July 2025, suggest that neutrinos may exhibit unexpected oscillation patterns, potentially hinting at new physics beyond the standard model. These experiments, grounded in meticulous data collection and analysis, demonstrate Fermilab's commitment to tackling the universe's deepest questions, moving beyond speculative rumors to deliver concrete scientific progress that could redefine our understanding of reality. The pursuit of knowledge at Fermilab is not a solitary endeavor, but part of a global network of collaboration that amplifies the impact of its research. Physics is inherently a collective enterprise, with scientists, engineers, and institutions worldwide working together to design experiments, share data, and validate findings. Fermilab's partnerships with organizations like CERN, Google Quantum AI, and universities across the globe have been instrumental in advancing projects like the wormhole simulation and DUNE, for instance. The Sycamore quantum processor, developed by Google, was a critical tool in Lickens' wormhole experiment, showcasing how industry and academia can unite to push scientific boundaries. Similarly, DUNE involves over 1,000 researchers from more than 200 institutions in 30 countries, reflecting the scale and ambition of modern particle physics. This collaborative spirit extends to the open sharing of data and results, ensuring that discoveries are scrutinized and built upon by the global scientific community. As of July 2025, Fermilab's contributions to international efforts, such as the Global Dark Matter Search and Neutrino Oscillation Studies, are helping to construct a more complete picture of the universe. This collective approach not only accelerates discovery, but also reinforces the credibility of scientific findings, countering misinformation and fostering public trust. By working together, scientists are not just exploring the cosmos, but also demonstrating the power of human cooperation in the face of nature's most profound mysteries, inviting us all to share in the wonder of uncovering the universe's secrets. As of July 24, 2025, Fermilab and other institutions continue to invest in quantum simulation, recognizing its potential to explore exotic physics safely. These simulations don't just test theories, they prepare us for future discoveries. By modeling black holes, wormholes, or vacuum decay, scientists can refine our understanding of the universe's fundamental laws. They can also assess the risks of high-energy experiments, ensuring that humanity's quest for knowledge doesn't endanger our existence. The code for these simulations, like the one used in the wormhole experiment, represents a key to unlocking the cosmos's deepest secrets. What's next? As quantum computing advances, we may simulate entire universes, testing theories of quantum gravity or multiverse scenarios. These digital laboratories could reveal whether our universe is one of many, whether space-time has hidden dimensions, or whether phenomena like cue balls could exist in nature. The journey is just beginning, and each discovery brings us closer to understanding the fabric of reality. The rumors of a hole in the universe may be unfounded, but they reflect humanity's insatiable curiosity about the cosmos. Fermilab's work, from quantum simulations to neutrino experiments, is pushing the boundaries of what we believe is possible. These efforts remind us that science isn't about chasing sensational stories, but about uncovering truths through rigor and evidence. As we continue to explore the mysteries of space-time, quantum fields, and the universe's origins, we invite you to join us on this journey. Stay curious, question boldly, and let's uncover the wonders of the cosmos together.